Okay, very good. So I guess it's time. So I am very glad to present Paul Nelson from the ETH Zurich and his talk on the orbit method, microlocal analysis, and applications to L functions.
All right, thanks very much, Dima, for the invitation to speak here and everyone else for coming today. So as you can see, my talk will be about applications to L functions using the orbit method as developed in the spirit of microlocal analysis. And so I thought that for this talk, I would do these in the order indicated in the title. So first, what are some objectives? We want to more specifically estimate L functions and averages of L functions on groups like products of general linear groups, maybe of ranks differing by 1, and groups like that, such as unitary and orthogonal groups. Part of the task that we face in doing so is in determining asymptotics of special functions attached to representations of such groups. We'll talk a bit about that. There's been quite a bit of work, particularly in the case when n is 1 for this problem by Bernstein-Reznikov, Akshay Venkatesh, and other people. So we're going to be kind of using maybe their general method, and the interest here will be applying it in a higher rank situation. And part of the way we address the special function analysis will be by developing the orbit method in the spirit of microlocal analysis. And then we'll apply all of this in the end to some standard problems involving L functions, such as moment problems and subconvexity. So that's just a quick overview of the main points we'll address. And we'll structure the talk as follows. We'll start by giving, I guess, a crash course on the orbit method or one viewpoint on it. And then I'll say a little bit about what we mean by doing microlocal analysis on Lie group representations. And then we'll talk about some of our applications, the local applications first, and then the global applications to automorphic forms after all of that. Okay, so we'll use the following notation. G will be a Lie group, frac G will be its Lie algebra, and frac G wedge will be the dual Lie algebra. So for example, if G is the general linear group, then there are standard identifications of both its Lie algebra and its dual Lie algebra with a space of n by n matrices. So the definition that kind of gets the orbit method starting is that of a cogent orbit, which is just a G orbit inside the dual Lie algebra. So the group G here is acting on itself by conjugation that differentiates to the adjoint action of the group on its Lie algebra and then dualizes to what's called the coadjoint action. And the orbits for that action are what are called cogent orbits. So for example, in the example I indicated earlier, these are the conjugacy classes of matrices, which we know are interesting objects from courses we've taken or taught on linear algebra. And these are generalizations of those objects that have some rich structure. A simpler example than the example I just gave is that of the group SO3. So it gives us a chance to draw some pictures illustrating some of the things we'll talk about today. So for that group, there are standard identifications of its Lie algebra and the dual Lie algebra with Euclidean 3 space, which we can make in such a way that the action of the group is just the usual action by rotations on 3 space, preserving the usual Euclidean metric. And then the coadjoint orbits are just the orbits for the rotation group. So those are the spheres in 3 space, and I've drawn some pictures of them here. So the first one you can barely see on the left here, that's the radius 0 sphere, the little dot. The rest of the spheres have a positive radius, and they look something like what we've drawn here. And yeah, I guess the theorem that gets the whole industry started is the observation that any coadjoint orbit naturally has the structure of a symplectic manifold. So it's not important for us to recall what that means exactly, but a symplectic structure is some alternating form on tangent spaces satisfying some conditions. A Lie algebra structure is also an alternating thing from the Lie algebra to itself satisfying some conditions. The conditions turn out to match up. So that's the observation here. The closeness condition matches up with the Jacobi identity. And in particular, there's a canonical notion of volume on any coadjoint orbit for any Lie group. So you can always make sense of the volume of a subset of such a coadjoint orbit. So we'll call that volume form omega. Okay, so those are orbits. What is the orbit method in a nutshell? Well, I guess you could describe it as a heuristic based on an approximate bijection between, on the one hand, the set of irreducible representations of your group, and on the other hand, the set of coadjuvant orbits for that group. So when such a bijection exists, at least approximately, we'll denote it by pi mapping up with opi. And of course, it shouldn't be just a random bijection, like a coincidence of cardinalities or something like that. It should be compatible with all the natural operations you can think of that you routinely use when you work with representations or with orbits. So the natural operations on representations like restriction, induction, tensoring, things like that, should all have natural analogs at the level of coadjuvant orbits. So one particular compatibility between the orbit and the representation is that the orbit should describe the character of the representation. So the character chi pi is a function on the group describing the trace of the action of group elements on the representation. And for small group elements, meaning group elements near the identity, well, we can write those elements as exponentials of small Lie algebra elements. And the requirement here is that the character evaluated on such exponentials should be given in a very straightforward way in terms of the coadjuvant orbit. So the formula I've written on the left-hand side here has two parts. The first part is not very important for our purposes. It's this Jacobian factor that I've indicated, which is normalized to take the value 1 at the origin. So the more interesting part for our purposes is the second factor, which is, you can say in a nutshell, just the Fourier transform of the symplectic measure. So you integrate the variable I've called xi over the orbit with respect to the canonical measure, and then you insert this Fourier phase. This integral computes the character. That's the main requirement. So whenever you have an identity like this, it's called the Kirillov formula. It's named after him because he gave the first kind of example of this way of writing down the character formula for the class of nilpotent groups. And since then, there's been a huge amount of work generalizing this to other groups. So I'll just mention the case of reductive groups and tempered representations, which is the one that we'll use most critically in our work. And the one thing I just wanted to mention that's kind of a, if this is your first time seeing this formula, you can evaluate both sides of the identity element of the group, or in other words, at the origin in the Lie algebra. And in that case, well, okay, the character evaluated at the identity element, we know computes the dimension of the representation. Whereas the right-hand side of this formula, the Jacobian factor goes away and the Fourier integral simplifies to just the volume of the orbit. So there's some identity between the dimension, which, at least for compact groups is an integer, and the volume of the orbit. And we'll come back to other ways to think about this identity a little bit later. So finally, I wanted to give one just very basic example that we can again stare at. So returning to the example of the group SO3, where we noted that the orbits are classified by the non-negative reals corresponding to the spheres. We might also know that the representations are classified by their highest weights, which we can normalize to be non-negative integers that I'll call T. And in this case, it turns out that the classical formula for the character of such a representation can be formulated by saying that the Kirillov formula on the previous slide holds if we define the coadjuvant orbit OPI to be the sphere whose radius is 1/2 more than the highest weight of the representation. And in that case, the volume of the orbit, of course, has to match up with the dimension of the representation, which in this case is 1 more than twice the highest weight. So you can take this as the definition of the kind of an ad hoc definition of this volume form omega. It's the rotation invariant volume form of this volume. So it grows a bit slower than the usual Euclidean volume as a function of t, but it's something very explicit. And now I guess you might complain, depending upon how you interpreted my phrase approximate bijection, that these two sets are very different. The set of irreducibles is classified by this discrete parameter, a non-negative integer, the set of orbits by a continuous parameter, this non-negative real. But I guess this is secretly an analytic number theory talk. Those are what our applications will concern. And in analytic number theory, you routinely kind of blur your eyes, squint a bit, zoom out, and try to see things in a big picture way where the dots on the integer line will blur together and look quite a bit like the real line. So for analytic purposes, this is quite close to a bijection. If you're going to do an average over a bunch of such representations, this is quite close to a bijection. Are there any questions so far? Okay, so I thought I'd end this first part just by giving one more fun example that shows up a lot when you study classical modular forms on GL2. So if G is the group PGL2R, you can think about elements of its dual Lie algebra as traceless 2x2 matrices. The coadjoint orbits, aside from the degenerate one consisting of just the origin, are classified by their determinant. There are two classes of such orbits, the one-sheeted and two-sheeted hyperboloids that I've drawn here and denoted here. And there are also two classes of tempered irreducible representations. So there's the principal series and the discrete series. And again, you have a very simple correspondence. The principal series corresponds to the orbit with parameter r, if r is its parameter. And for the discrete series, you just have to shift by a half again, like for the group SO3. So I just mentioned this because a lot of, for anyone thinking about analytic number theory of modular forms on GL2, this can be a very useful picture to keep in mind for the special function analysis that comes up. So I've spent a lot of time thinking about pictures like this in such situations. Okay, so now I wanted to talk a little bit about microlocal analysis. So starting from the beginning, what is microlocal analysis in its traditional sense on, say, Euclidean space? So this I'll try to summarize as the art of taking an arbitrary function, perhaps, on Rn, and trying to decompose it in a useful manner into pieces that are localized in both position and frequency. So maybe the most ambitious localization you could imagine would be, say, that they're both compactly supported in position and frequency. But of course, we know that there aren't any interesting functions with that property. But you can settle for, say, weaker versions of localization. For example, you can ask that the function have most of its mass concentrated near some particular point and have its Fourier transform have most of its mass near some other point in the Fourier domain. And so a good example of a function that kind of splits the difference between concentration and position and momentum is a Gaussian, or more generally a modulated Gaussian, as I've written here. So this is a Gaussian modulated by a point x naught, translated by a point x naught in position space, and then further modulated by a point xi naught in Fourier space. And so what we get from this is a function that decays very rapidly outside of a small neighborhood of the point x0. And if you work out what the Fourier transform of this Gaussian is, it has a very similar shape, but the roles of x and xi are kind of reversed. So that Fourier transform Gaussian will concentrate near the Fourier point xi naught. Now, the way that one actually carries out microlocal analysis in practice is through what are called pseudo-differential operators. So I've denoted these op of A. These are operators on various spaces of functions on Rn that are attached to functions, or what are typically called symbols, that I'll call A, which should be thought of as functions of these two variables x naught and xi naught that we started with here. So we can think of that pair maybe most canonically as living in the cotangent space of Rn, or more concretely just as a 2n tuple of real numbers. And I think, there are many ways one can write down a definition of a pseudo-differential operator, but the motivating maybe characterization of these definitions is that these operators should be approximately diagonalized by the functions that are localized in both position and frequency. So for instance, Gaussian, when we act on it by a pseudo-differential operator with symbol A, it should be approximately the same Gaussian again, at least something of a similar shape, multiplied by the eigenvalue given by evaluating the symbol at the point where we're localized. And so, for example, once one has a nice, well, first definition and then calculus of pseudo-differential operators, one can do things like decompose functions by starting with the constant symbol 1, just the constant function, for which the corresponding operator is the identity operator, and then maybe applying a partition of unity to this constant symbol. And this then gives a partition of the identity operator as an infinite sum of operators, each of which we can think of as projecting onto a space of functions that look kind of like this modulated Gaussian, that'll concentrate in some small part both of position space and frequency space. So that's an overview of microlocal analysis in Euclidean space. We're going to work with microlocal analysis on a representation of a Lie group G, which I guess is kind of a philosophically not so surprising analog of what we've discussed above. And it's very closely tied up with the geometric quantization industry. So I can't give an exhaustive history here, but it's basically in a nutshell, the art of, again, decomposing vectors in a representation into pieces that are again localized in a suitable sense, where suitable can be taken to mean here being approximately eigenvectors of certain parts of the group G. So sufficiently small elements in that group should act in a predictable way on such vectors. Now, how more precisely might one develop such a theory? So one needs an analog of the pseudo-differential operators. So for our purposes, such an analog is given just by the integral operators on the group. So we'll take a smooth function supported very close to the identity element in our Lie group, and we'll integrate out that function against the representation to define an operator. To be able to work usefully with such operators, we need to parameterize the functions in some way. And the way we'll do that is through basically their Fourier transforms. So a bit more precisely, we want to work with abelian Fourier transforms, and the group G is typically non-abelian. So we'll do the naive thing where we take the function, we pull it back to the Lie algebra. This is something that makes sense because it's supported near the identity. So we'll pull it back, we'll get a function on the Lie algebra that's now supported near the origin. And then we'll think about such functions in terms of their Fourier transforms, which will now be Schwartz functions on the dual Lie algebra. So those Schwartz functions in the dual Lie algebra we'll refer to by A. And just as a matter of notation, so that we don't have to repeat the 5 lines on this slide very often, we'll write op of A for the integral operator pi of f attached to such a function. So f and a are related by a Fourier transform in kind of the only conceivable way in our setup. And when that's the case, we'll write op of a for the integral operator attached to f. And it's useful at this point just to kind of tie this up with what we talked about in part 1 by noting that the trace of one of these operators is given up to these Jacobian factors that I said we'd basically ignore by integrating the symbol A over the coadjuvant orbit with respect to its symplectic measure. So this again is very similar to what one gets in the theory of pseudo-differential operators, where the trace of such an operator is given by its integral over phase space, the cotangent bundle of your manifold. Okay, now we'd like to translate into this group setup the heuristic that we mentioned on the previous slide about how we can think of microlocal, or how we can think of microlocal analysis and these operators as corresponding to a way of splitting up vectors into pieces that are localized. So we'll try to motivate that through the following heuristic. The heuristic is as follows. Anytime we have a partition of our coadjuvant orbit into partition elements that I'll call p tau, where each of these partition elements has volume 1 and is concentrated near some element tau in the cogent orbit. I'll give a picture on the next slide to let us visualize this, but okay, anytime we have such a partition, there should be at least approximately a corresponding orthonormal basis for our representation. So the representation should break up as a sum of lines spanned by some vectors that I'll call v tau. And so the vectors v tau should match up with the partition elements p tau in some way I'll describe in a second. And we can think it for a second that, at least at the level of cardinalities, such a bijection makes sense and should exist, because we've noted earlier that the dimension of the representation, in other words, the number of vectors that'll show up here, is the same as the volume of the cogent orbit. And so if each piece in our partition has volume 1, the number of partitions is also the volume of the cogent orbit. So we have two sets that we're talking about here, each of the same cardinality, and we're just saying that there should be some natural way to biject between them. And the precise way is kind of the only way that one can imagine in retrospect. It's that if we take these operators op of A that we defined in the previous slide, they should behave compatibly with respect to the two sides of this correspondence. So given such an operator, we can interact with it on this side by having it act on a vector. And the assertion is that, well, what can we do with such a symbol A on this side? We can evaluate it on a partition element. So let's just write A of tau for the value it takes on, say, the base point tau of that partition element. And so the assertion is that these operators should be approximately diagonalized by these bases, and their eigenvalues should be approximately the values they take on the corresponding partition elements. And of course, for any of this to make sense at all, we need for our symbol A to be essentially constant on the partition element. Because certainly this left-hand side is insensitive to what we choose our base point tau in our partition element p tau to be. So the right-hand side should likewise be insensitive. So provided we can assign one number to the value of A restricted to p tau, we should have some approximate diagonalization property like this. And when this is satisfied, we'll refer to the vector v tau as localized to the parameter tau, and we'll call p tau its microlocal support. And this is again in strong analogy to standard terminology in the theory of pseudodifferential operators. So I wanted on the next slide to state a theorem kind of informally that appears in our papers that you can think of as basically saying that this heuristic is true in a sufficiently usable sense for analytic purposes. Before I get to the theorem, I wanted just to draw a picture that kind of illustrates what's going on in our running example. So if our group G is the group SO3 and pi is one of these highest weight representations that we recalled earlier, it turns out the right size for a partition element is that it should be roughly a big O t to the half ball inside the cogent orbit surrounding one of the elements of the cogent orbit. So here I've drawn a partition of these spheres into small triangles. The shape of the triangle isn't important at all. I just wanted to have some kind of visual representation. We should think of each of these triangles as being like maybe a fuzzy blob that's approximately a volume 1. And the radius roughly of each of these triangles is roughly t to the half. And the numerology works out now that there are roughly 2t plus 1 such triangles with this radius inside this sphere. So as the sphere gets larger and larger, I mean, you can see that there are many more triangles in the right picture than the left picture. And so if we kind of zoom our camera out sufficiently far back that the sphere stays about the same size as we increase t, the triangles get denser and denser. They form a very fine partition of the sphere, and we approach some kind of continuum limit as t goes to infinity. So now I wanted to comment finally on this slide. I mentioned on the previous slide this condition that this correspondence only makes sense if A is essentially constant in each partition element. So what does that condition translate to here? Let's say we're a little more aggressive and we want for the symbol A to be not just constant, but to vary by, let's say, at most t to the negative epsilon for some positive epsilon on such a partition element. Then I guess the reasonable condition to write down is the following derivative bound on the symbol A. So if its derivatives grow slower than a bit smaller than t to the negative half, then when we multiply, for example, the first derivative bound for A by the radius of these partition elements, we see that the symbol A indeed varies by something quite small on each such partition element. Okay, any questions so far?
Can I ask a question? Like,
yeah, sure.
So about like this approximate eigenvectors. So is it like the approximation is as good as possible? Is better if the partition is smaller or like or is finer or coarser? Like it's.
So there's kind of a canonical scaling of the partition for each representation. So for each representation, so I've indicated two possibilities here with different values of t. As the size of the highest weight in this case increases, the size of the sphere increases, and you get more partition elements. But in each case, there's a canonical normalization. Each partition element should have symplectic volume roughly 1. That's the right condition for it to match up to a vector. Does that make sense, or does that answer your question?
Yeah. So it's like the volume of partition should be like roughly the same, but like so as you so like go between, like, I mean, as you look at different orbits, like so there are different numbers of partitions. Like you're not changing the size of okay, got it. Yep, thanks.
Yeah, and kind of, I mean, the thing to think about is like imagine zooming your camera out or scaling your orbit down, even though the orbit's actually increasing, then you get more and more partition elements, and you can kind of think of it as being a continuum limit. This is,
all right.
Yeah.
Thanks.
Sure. Okay, any other questions? All right, so the theorem that I've tried to summarize. I mean, this might be something like 10 very technical theorems spread across 2 papers that I'm trying to summarize in a non-technical way on this slide, just to give the flavor. And I mean, hopefully the non-technical summary is more useful than trying to make it very precise. But I mean, let's just walk through it. But like I said, the theorem basically says that this heuristic picture can be implemented in a useful way. So we'll consider, here's one way to formulate it. We'll consider a sequence indexed by parameter t of unitary representations of a Lie group. So we have an assignment that we defined earlier from functions to operators that we're going to restrict to functions that satisfy the same estimates as on the previous slide. So I've copied them here, for example. And then the assertion is that these enjoy some reasonable microlocal calculus. So for example, so I've just summarized the conditions again here. Let's say that our symbol A is supported on elements of size roughly t and satisfies the same derivative bounds as motivated in the previous slide in order for it to be roughly constant on each partition element. So and then in that case, the corresponding operator should have operator norm big O of 1. And this is not so surprising, or it shouldn't be so surprising, because heuristically, we've suggested that these operators should be approximately diagonalized by a basis of microlocalized vectors, and the eigenvalue should just be the values of the symbol at the corresponding points tau. So heuristically, op of A is a diagonalized matrix with entries of size big O of 1, so its operator norm should be big O of 1. And this just makes that precise in a manner that's kind of, it's an analog of the Calderon-Valencourt theorem from pseudo-differential operators, and it's very similar to that. We have an analogous assertion for trace norms that says that they grow kind of at the rate that they should in terms of invariance of the orbits. We also have a result, it's a composition formula that we can think of as, maybe the first order is just saying that these operators approximately commute, which is something we would reasonably expect given that heuristically they have a common eigenbasis. And then finally, we have similar results for, for example, polynomial functions or more general symbol classes, and also for functions with less regularity transverse to the coadjuvant orbits. So in the setting of the previous slide, this will be a function that maybe is highly irregular in radial directions, even though along each sphere, it satisfies the same regularity that we stipulated. So this last condition is what is contributed in this more recent preprint. Okay. So, yeah.
I'm a little confused about the dimension.
Sorry, where do, yeah, the dimension, sure.
Is the dimension of your orbit is maximal? Is this the regular orbit or?
Yeah, so I should have said here that pi is irreducible and tempered. That is part of part 2.
Then I have no objection.
Yeah, thanks. Yeah. Yep. All right. I should mention also there are papers of Roger Howe, I think from the 70s, that basically do an analog of this all for p-adic groups, where you don't have to wave your hands and say approximately in every other sentence. You can just say literally, and it's a very similar statement with all identities. So one can think of this as kind of giving an analog of type theory in some asymptotic sense for real groups. Okay, so if there are no other questions on the first couple parts, I wanted to kind of proceed to the applications, starting with the local ones and then going to the global ones. Yeah, Dima, I think you told me this is a 1-hour talk. Is that right?
That's okay, but you can use a little bit more.
Okay, I'd be very happy with an hour, and then I'd be happy to chat after.
And also, I would like to verify, the first part is completely general, isn't it?
Yeah, this is general. This is just, we're just, you could say, studying the Heck algebra on a Lie group near the identity and thinking about the asymptotics, except I guess in this part where we're using the character formula to quantify things like trace norms. Yep.
Thank you very much.
Sure. Okay, so yeah, we'll give some local applications now to so to the following problem in, I guess you could say, asymptotic representation theory. So I'll let G and H be one of the following classes of groups. So you can think of these conceptually, if you'd like, as the strong Gelfand pairs over the reals. Yeah, I mean, I guess the complex groups would also be fine for our purposes here. Yeah, maybe it's off-putting that I've given 3 examples. You can choose whichever one you want that is simplest for any given slide of the talk. So GLN is simple for many purposes, but sometimes it's simple to pretend that you're working with a compact group. And in that case, you could take the compact unitary groups or the compact special orthogonal groups, and those are all fine. Okay, so yeah, I mentioned that they have a strong Gelfand property, which, well, I guess a strengthening of that property asserts the following. Let's take a tempered representation pi of our group G, of the big group. And let's think about the restriction of that representation to the smaller group H. Then the assertion is that there's some sense in which we can decompose this as a direct integral of, again, tempered irreducible representations of the smaller group H, where each of these representations will appear at most once. That's kind of the content of this Gelfand property. And I guess the usual thing that one means when one says direct integral decomposition, it ends up boiling down to some kind of Parseval type relation describing the norms of, let's say, smooth vectors in the representation. in terms of the norms of some vectors in sigma, the representation of the smaller group, that you get by projecting in some way the vector in the representation of the bigger group. And whenever you have a direct integral decomposition, you have some ambiguity in choosing the measure with respect to which you decompose inside its measure class. So one can normalize it so that it's given by the Plancherel measure dual to a given Haar measure on the group H. So an example that's good enough for our purposes here would be when, say, G and H are compact, say, special orthogonal groups, maybe SO3 and SO2. In that case, we're just saying here that you can decompose the restriction as a direct sum with multiplicity 1 of irreducibles of the smaller group, and then you can write norms of vectors in terms of norms of their components. Now, these projections are not quite well defined individually. I guess they're defined maybe up to some sign, so some complex number of magnitude 1. But the norms here are some completely well-defined numbers that we can attach to any, say, smooth vector in the representation of the big group and any tempered representation of the smaller group that shows up in this decomposition. So we're going to formulate a problem that's motivated by our applications to L functions that we'll talk about in the last part of the talk, which is about these numbers here, the numbers you get by looking at the sizes of the projections. So the problem is well, here's kind of a loose formulation of it. We'll make it more precise on the next slide. Let's start with some nice family of representations of our smaller group. By nice, maybe we describe our representations in terms of their numerical parameters, and we ask that each of these numerical parameters lies in some nice region, some nice product of integrals or something like that. And the problem I'd like to talk about is, can we construct a nice vector in the representation of the bigger group G so that the numbers we get by computing sizes of components pick off the family F? So they should be roughly 1 if the representation of the smaller group lies in our chosen family, and they roughly vanish if it doesn't. Now, I guess this is not quite a completely well-formulated question because I didn't say what nice means and I didn't say what construct means. And depending upon what functional analysis we consider available, the answer to this question is surely yes. If F is, say, a measurable family, you can find a measurable vector that looks however it wants to with respect to this direct integral decomposition. But we want to really construct the vector, and we want it to be a nice vector that we can maybe access in some other way. More precisely, we'd like to understand how the group G acts on such a vector. So one way to formulate the nice and construct parts of the question is by asking, let's say, can we estimate the matrix coefficients of the vector? Not just under the group H, but under the full group G. So, I mean, we could debate whether it's an interesting question, but at the very least, it'll show up in our global applications. On the next slide, I want to kind of reformulate this question in terms of what are sometimes called the relative characters attached to pairs of representations of these groups. But maybe before I do that, are there any questions about what I've written here? Okay. Oh, and I should have said at the beginning of the talk that I like to be interrupted, so feel free to ask questions even if I'm not offering that. Okay, so relative characters. Let's define them as follows. Start with a tempered pair of representations, pi and sigma, of the big group G and the smaller group H. And let's consider the Hermitian form that I'll call H sigma. It'll be a Hermitian form on the representation pi of the bigger group. And it's simplest to describe it on the on individual vectors as just the norms of these projections that we defined earlier. You can erase the word local. That's a typo here, or it's not necessary. So one way we can package these Hermitian forms together is by viewing them as distributions on, well, on the Lie group, or for our purposes, more usefully on the dual Lie algebra. So given a nice function A on the dual Lie algebra, for example, a Schwartz function, we've defined these operators op of A that we get by taking a Fourier transform and then taking the corresponding integral operator. And we'll define a relative character, h of pi sigma, to be the distribution we get by averaging these Hermitian forms in the only conceivable way. So we take an average, or we take a sum over an orthonormal basis for our representation. We apply our operator to the first copy of our vector. We tensor with the second copy, and then we evaluate under this Hermitian form. And just to give a kind of heuristic way to think of this, maybe let's consider the case where A is roughly our characteristic function of one of the partition elements, one of these little triangles in our pictures from before. So in that case, well, this sum can be computed using any orthonormal basis. So we might as well compute it using a basis of localized vectors, v tau. But if A is a characteristic function like this, then by the basic way we characterize these localized vectors, it'll kill all of the elements in our localized basis, but the one vector v tau localized at this particular tau. So the whole sum will collapse to a single term with just v tau tensor v tau, and we're left with just the size of the projection of v tau to sigma being what this computes. So you can think of these relative characters as packaging together as a distribution the sizes of the projections to representations of H of all of the localized vectors in our representation of the big group. So the question we'll ask now is, let's let AA depend upon a parameter t, and let's let it vary as in the microlocal calculus theorem that we stated a few slides ago. And let's also allow the representations pi and sigma to vary, maybe in a completely unconstrained way for now. Then what can we say about the asymptotic behavior of this relative character? Now this question is obviously directly useful for addressing the motivating question on the previous slide. Because if we can understand the sizes of projections of vectors to sigma in a simple enough way, then I think we can imagine that we can, using very specific choices of tau, we can cook up some such vector that picks off the family of representations sigma that we're interested in. So this is maybe the precise form of the question on the previous slide. Are there any questions about what we have here so far before we go on? So the orbit method says that to understand a question like this, you should maybe first consider the corresponding problem involving coadjuvant orbits. And here what we're doing is we're trying to measure how the representation pi and the representation sigma, after we do some restriction, the corresponding problem at the level of coadjuvant orbits is to take the coadjuvant orbit of pi and intersect it with the coadjuvant orbit of sigma after pulling it back to the Lie algebra of the bigger group. So by analogy to the notation on the last page, I'll write O pi sigma for this intersection. I've given some pictures of such sets below here. These are the one-dimensional sets that kind of zip around the sphere in this picture. So here O pi is the sphere. O sigma will be a point lying on a line. And the intersection will be one of these, well, either the equator or some strip that you get by intersecting the sphere with some horizontal plane. And here, each of these little one-dimensional hyperbolas on this hyperboloid is another example of an O pi sigma. Now, there's an important condition on pi sigma that we single out here. So we'll call the pair pi sigma stable if O pi sigma is an H-torsor, meaning that it has closed orbit in trivial stabilizer. So the terminology is motivated by the fact that, well, I guess in these examples, trivial and finite are equivalent at the level of stabilizer. So this is the standard terminology from geometric invariant theory for the stable elements for, in this case, the action of H on, for instance, OPI. Now it turns out that this condition of stability on the pair pi sigma is a generic condition, meaning that it's satisfied for almost all pairs pi sigma in terms of their parameters, for instance. And in fact, it only depends upon their infinitesimal characters, which we'll call lambda pi and lambda sigma. And in terms of those, it can be expressed as the condition that none of the eigenvalues of one infinitesimal character match up with any eigenvalue of the other one. So in this picture here, where is the stable locus? It's away from the north and south poles of the sphere. I mean, you can imagine that at the north pole here, there's some, you know, if there existed a sigma that picked off that point, its stabilizer under H would suddenly jump from being trivial, which is what it is, say, at the equator, to being the whole group H at that point. And so it would acquire additional stability. And this is also the point where the parameter of the representation sigma would be the same as the highest weight of the representation pi. So there's a coincidence between the parameters colliding and stability failing. And the same thing happens in this picture around this cross, I guess for slightly more complicated reasons. There's both failure of trivial stabilizer and failure of closed orbit at points here. But generically, you get these nice torsors here. So our theorem says the following: if we take a sequence of tempered representations, depending upon a parameter going off to infinity, which satisfies a condition that I'll call uniformly stable, meaning the stability characterization on the previous slide in terms of the infinitesimal characters, after we scale them down by this normalizing factor t, should hold with a bit of room. So it should hold in the sense that this rescaled parameter lies in some fixed compact collection of stable pairs of parameters. So in terms of the previous slide, we just want to stay away from the poles of the sphere and away from this x on the hyperboloid with our set OPI sigma. Now assuming that condition, the theorem will say that if we take a symbol A as in the microlocal calculus, so satisfying the same derivative bounds that we summarized there, the relative character will be asymptotic to the integral of the symbol over this intersection of coadjuvant orbits. And the stability condition gives a natural way to actually say what this integral means. We remember the stability condition says that this domain is a torsor, so we can integrate it over it by transporting the Haar measure from H. So here's a typical picture where OPI is the sphere, OPI sigma is the equator. And it says that, for example, if we take a localized vector on the sphere corresponding to some little blob in some region, we can compute how much mass it projects onto, in this case, the trivial representation of H by just computing the size of the intersection of the equator with that blob. That's the informal content of the theorem in the case that A picks off a localized vector. Okay, so I'll just say a couple words about the proof just to kind of tie it in with what we've talked about before. I mean, the first step is we can write down a formula for these relative characters in terms of traces of operators and their translates and characters of our representations. We can reduce basically by integration by parts to the special case that the symbol A is concentrated near some partition in our partition of the coadjuvant orbit, which lies in this intersection of coadjuvant orbits. So away from this, there's kind of free decay just from integration by parts with respect to the action of the center of the universal enveloping algebras of G and H. And in that case, the integrand, or the interesting part of the integrand, is just a matrix coefficient of one of our localized vectors. And that's because op of A is roughly a rank 1 operator attached to such a vector. And this matrix coefficient will be negligible unless the group element approximately centralizes the parameter tau. Basically, because this correspondence between parameters and localized vectors is equivariant, and these localized vectors attached to disjoint blobs are roughly orthogonal from one another. So that gives this kind of decay of matrix coefficients. But we've assumed we're in this stable situation where H has trivial stabilizer acting on tau. So the centralizer of tau in H is trivial. So the only way that this condition here can happen is if H is very close to the identity element. And in that case, we can basically expand everything by brute force using Taylor series and the Kirillov formula from before. So to give the actual proof is obviously much more technical, but just in a few words, it comes from taking these localized partitions and considering the sizes of matrix coefficients of localized vectors in conjunction with the stability hypothesis on the parameter tau. Okay, so now I'll say a few things about global applications to L functions. So I'll need a little bit of notation. We'll continue with G and H as before. So maybe GLN plus 1 and GLN over the reals. And we'll need now, we'll talk about automorphic forms, so we'll need some lattices, maybe gamma and gamma H inside G and H. And we'll write brackets G and brackets H for the corresponding quotients. Most of our results will be about the cases where these quotients are compact. And we'll focus on representations that are at least tempered at in this case, the Archimedean place. It's probably better for all of us to work with Adela quotients. That's what we actually do in our paper. And then we single out a single real place of some number field, but I'll present it as if we're working over the reals and the integers. Okay, so the refined Gangros-Prasad conjecture, or the Achino-Ikeda conjecture, which is known now in many cases, I've said it here maybe in a slightly unusual way, but it ties in with our notation. Let's break it down. So on the left-hand side, we have some integrals of automorphic forms. So here V is an automorphic form in the representation pi, U is an automorphic form in the representation sigma, and we take some integrals of them. So here V integrated against U bar, here V bar integrated against U. We've applied an operator to one of them, but ignore that for now. So informally speaking, this conjecture says that such integrals are given by this number I've called L of pi sigma, which will be the special value of an L function, times some local integrals in terms of, defined in terms of the vectors, usually by integrating a matrix coefficient. So I've written it this way because when you sum over the vectors and you apply the operator in the way I've written here, the local integrals that you get on the right-hand side are just exactly the relative characters that we defined in the previous section. So these relative characters show up very naturally in the setting of the Gangros-Prasad and Achino-Ikeda conjectures. I've given here a simple example of what these things look like. So in the GLN-Z case, they look like squares roughly of Rankin-Selberg L functions. In the unitary case, they're base change L functions. So these are numbers that are of interest to estimate either individually or in an average sense to analytic number theorists. And I guess this formula suggests a way to try estimating them, at least on average. So for example, maybe you want to understand the average of this number L of pi sigma as one of your representations goes over some family. Maybe pi goes over some family and sigma is fixed, or vice versa. You could try doing that by choosing your symbol A so that the relative character detects the characteristic function of your family. and then understanding the sum of the left-hand side over all pi or over all sigma unconditionally. And that's something you can try doing. I mean, for example, if you sum over sigma on the left-hand side, you can try understanding that using the Parseval relation on the quotient of H. And if you try summing over pi on the left-hand side, that's something you can try studying using, say, a relative trace formula for the group G and the subgroup, well, I guess H and H acting on it. Okay, so I'll try stating the global results now. So maybe we're in the general linear case, just to kind of focus ideas. Let's take pi to be, say, a cuspidal representation of GLN plus 1. We'll take everything here a full level, so there will be no interesting ramification outside of one Archimedean place. And let's write maybe T1 through Tn plus 1 for the Archimedean parameters of pi. So the results are valid for any pair of tempered representations, but maybe pretend it's a principal series representation and these are real numbers just to kind of focus ideas. And then we'll have the same thing on GLN for some representation sigma, which will now have n parameters that I'll call U1 through UN. So then there's some tensor product, I guess L parameter with whose local parameters will be obtained by summing all of the pairs from these two sets. And now we're not actually going to prove anything in our papers about kind of the non-compact setting. We're going to do everything for an anisotropic pair of, for example, unitary groups, so that our automorphic live on compact quotients. So this is the setting in which all of our results are actually proved, but the parameterization is like in this setting here. Okay, so then two theorems. So one is this theorem joint with Venkatesh that we posted on the archive I guess in 2018. So it says that if we fix the representation of the bigger group and average the L function over all representations of the smaller group whose parameters lie in some big dyadic window, we get the expected constant. Well, I mean, I guess first of all, we prove an asymptotic formula, and we check that it's the thing you'd expect coming from standard heuristics for averages of L functions. Okay. And the second theorem, which I put on the archive near the end of last year, well, I'll formulate it as two parts. So on the one hand, we prove something similar to this average result, but the roles of the two representations are reversed. So we fix the representation sigma on the smaller group, we sum over pi on the bigger group, and okay, rather than summing over a dyadic family, we sum over a short family. So maybe take each of the parameters to lie in some interval of length 1 rather than some big dyadic interval. And you can have a different interval for each parameter, but they can be of roughly this shape here. But actually we proved something a bit stronger in part 1. So in this theorem with Venkatesh, this is actually an ineffective asymptotic formula. So we don't get any effective error term because eventually it's relying on Ratner theory. For this analog here, it's actually an effective error term. So we can put in a short amplifier, meaning we can weight our family by Hecke eigenvalues at some auxiliary places and retain an asymptotic formula. And so using that, we can get a better than trivial upper bound for the individual L functions that show up here under a condition. So this is a restatement of the uniform stability condition from our relative character theorem. So under the condition that all of these sums of pairs are roughly of size t, meaning I guess the key feature here is that they're bigger than some constant multiple of t. So this is a bound, this is known as a subconvex bound for an L function. So if we delete the delta there, this would be a trivial bound for the L function that one could deduce, or that I guess would be known by soft analytic techniques. So we get a very small savings over that. So I've simplified the exponent here, but it's something like 1 over n to the 5th times a constant. Okay, so the proofs combine, well, the relative character asymptotics from our local section with some additional global input. For the first theorem, as I mentioned, it's Ratner theory. For the second theorem, it's the analysis of a relative trace formula for this pair of groups. And yeah, just to finish on the hour, I will just show you what, for this second example, the analysis ends up boiling down to. So it ends up boiling down to a kind of nice linear algebra problem, which I've stated here about, well, it's not really about anything. It's about n by n matrices, and it asserts the insolubility of some explicit system of linear equations defined in terms of commutators of matrices, like so. So I guess you have the copies of the slides, so I can let you stare at that. And I'll just put the summary slide here now so that I can end on time. And I'll just say, yeah, so what we did was we developed the orbit method in an analytic form as a microlocal calculus that's sharp up to the epsilons that we put into this calculus. We applied it to determine these relative character asymptotics under this hypothesis of uniform stability. And then we deduced moment estimates and subconvex bounds for some families of L functions using some additional arguments. And so I have a couple bonus slides going into just a little bit more detail, some of these global arguments if people are interested, but I'll end the talk now. Yeah.
Okay, thank you very much. Questions, please.
What are the missing slides?
Okay. All right. Well, we just got a couple of them, right? So I guess we can just walk through them, right? So I'll talk about the proof of the second result here, where it involves analysis of a relative trace formula, because that's a more recent one. So let's remember, we have this correspondence between operators and functions on the dual Lie algebra. So pi of f is op of a. We're going to choose a very specific a. So we're going to take a supported near some element tau of this intersection of cogent orbits, and we'll take that element of size roughly t. So I've drawn here a dotted rectangle that indicates roughly the support of the function a. We should think of a as being roughly a characteristic function of that rectangle. So what's going on here is we're taking the cogent orbit of pi, we're taking a point in it that happens to project to the cogent orbit of sigma, and we're taking a very thin rectangle that kind of hugs this cogent orbit as tightly as one might expect it to. So it should have height t to the epsilon, meaning it should vary transverse to the cogent orbit by at most t to the epsilon. And then it should have width, this t to the half limit that comes from the Planck scale that we motivated in our pictures with triangles and stuff like that. Now we write down a relative trace formula for the corresponding function f. And I've written here what that looks like. So the geometric side we recognize as kind of the geometric side of a relative trace formula. So we have a sum over rational points of gamma. We integrate that against automorphic forms in our representation sigma of the smaller group, summed over a basis. And then I guess the choice of A has been rigged up so that the spectral side of that relative trace formula is the sum we want to compute. So it'll be a sum of these L values where we only sum over the family. The family is basically all of the pi's whose coadjuvant orbit looks very much like this one, up to imperceptible error. So for instance, if pi were a discrete series representation, this would be basically a sum over all representations of that type, of that particular discrete series. Now, yeah, we got to continue. So we got to analyze the right-hand side of the formula. we'll get a, so I guess the usual thing people do when they analyze these formulas is they break up the sum over gamma into double conjugacy classes with respect, or into classes with respect to the two-sided action of H. We're not actually going to do that here. We're just going to kind of crudely break it up into a sum over elements of H, which will give a main term that we won't say more about here. This is a term that we'll make smaller using Huck operators. And then the main point will just be to show that every other element gives a smaller contribution. And since F will be supported in a fixed neighborhood of the identity element of the group, and since our quotient of H is compact, there will actually only be more or less a bounded number of gamma that'll contribute. So we basically have to show for each gamma, once we choose a fundamental domain for our quotient of H, that this right-hand side is small. And moreover, we can get rid of the sum over U. So the sum over U, it turns out that the only U that really matter are the ones that are localized at the image of tau inside the cogent orbit of sigma. So let's call that image tau H. It'll be the restriction of this parameter tau to the dual Lie algebra of the smaller group H, and it'll lie in this cogent orbit. And then we're left with the problem of bounding these, what remains, this individual, more or less individual U, more or less individual gamma, and then we have an integral. So the feature that comes into play is that because U is localized at the parameter tau H, it has some kind of at least approximate equivariance under the centralizer of tau H in H. And if everything I've said so far is all that you're going to use about this last expression to bound it, you end up needing to bound an expression like this. This is what more or less Perron-Frobenius theory tells you about that last expression. Now, maybe so as not to give the longest possible answer to your question, I'll say that if you analyze this right-hand side, it turns out there are some special cases that it suffices to consider. And the problem boils down to exhibiting transversality between a particular pair of subvarieties of the cogent orbit. So I've indicated them here in the simplest case. So one of the varieties is this variety H tau. I guess it's also this variety O pi sigma we've considered earlier. Here it's the equator. And then here there's a translated copy of, well, in this case, just the equator again, gamma times the centralizer orbit of tau. And you want to know that these two orbits don't completely overlap with each other. So the numerology works out that the two varieties you're trying to exhibit transversality between have dimensions summing up to the dimension of the ambient variety. So there's a good chance that you could have literal transversality generically. You only need a little bit of that transversality. And so, I guess the picture on the previous slide is maybe a bit misleading because it's quite easy to see this transversality in the case of the sphere. It's just saying that if you take the equator and you translate it a bit, it's now transverse to the original equator. So I don't know, I computed numerically the extent to which these varieties were transverse in some examples where n was 5 and 6. And it turns out they're not always transverse. But there's at least one direction with respect to which they are always transverse. So if you take the direction in the centralizer orbit given by the center of the group H, so you're replacing that n-dimensional orbit with a one-dimensional orbit, you're now faced with a harder problem of exhibiting transversality between smaller varieties, but there's more structure in that problem because the center is somehow more structured than the centralizer. And then you can numerically compute, well, okay, first you can reduce the whole problem to a Lie algebra question. I guess even on this last picture, there's obviously a Lie algebra thing going on here. You can check the transversality infinitesimally. And then it reduces all to a linear algebra question here, which you can check numerically is always true. And then you're just left with the problem of proving that you're actually solving this linear algebra question, which you solve using, in a nutshell, the determinantal condition for insolvability of linear equations. So you can show a system of linear equations is insolvable if some determinant has a non-vanishing minor in the matrix describing the system of equations. So this theorem here is a restatement of the elementary theorem that I stated on the next slide, just in the more natural way it arises. Okay, so I hope I answered your question by showing the extra slides. But yeah.
Thank you.
Yep.
So do you need to use the Jacques-Rallis trace formula?
No, this is, well, it depends what you mean by use, but I mean, this is quite a crude thing we're doing here. So we're just writing down the, what is it called? The automorphic kernel function attached to F and integrating that over a compact quotient. So maybe this is a special case of the Jacques-Rallis trace formula, but it's not using anything interesting.
Then what is particular about unitary groups? So for instance, what about orthogonal groups?
That's a good question. So so in principle, yeah, so actually this theorem here is also proved for orthogonal groups.
I see.
I imagine this theorem could also be proved for orthogonal groups. The only, in fact, the only thing that's kind of in the way is that I've only worked out this linear algebra result for unitary groups.
I see.
So I've tried to write the paper in such a way that if someone wants to solve the corresponding linear algebra problem over orthogonal groups, then the theorem will pop out for orthogonal groups. Yeah.
But we don't know Gauss Prasad for the orthogonal case, right?
Oh, that's another important, yeah. So I guess the theorem for the numbers in the Chino-Kade conjecture, but not knowing that they're L functions.
I see. Thank you.
Right.
Sure.
Any further questions? Right, then let us thank the speaker again. And so now we will have a long Passover break. So the next seminar is on April 7, and it will be by Siddhartha Sahi on Fourier coefficients of automorphic forms. So see you in 3 weeks.
Happy spring break.
Cool. Same to you guys.
Thank you very much, Paul, for this wonderful talk.
Bye. Thanks.
Cool. Yep.
Bye. Happy Passover.